All right, now as you take a look at this problem, a couple things that I want you to notice right at the start about information we're given. One is the investment that we have here averages an increase of 11% per year. That percent is critical information here because anytime you are repeatedly increasing or decreasing by a given percent, we're going to be using that formula that we learned yesterday. That A of t equals P times 1 plus R to the power of t. Get to know it. It's going to come up a lot. Yes, you have it in your notes. Work on memorizing it so you don't have to rely on them every time. So then once we know that, then we can see the other numbers that are involved. Now, P, remember P represents principal. What would my value of P be in this particular problem? Principal means starting value. So my principal here is going to be the 1,000. So we're going to go 1,000. And then it's times 1 plus R. Okay, so what's the value of R going to be? 11%. Yes, but it's not going to be 11. Yep. Remember, we have to take the 11, we have to take whatever the percent is and divide it by 100 to make it as a decimal. So yes, it's going to be 0.11. And then it's to the power of t. What is t here? 42. Yes, because we're going from age 18 and going up all the way to age 6. So here is our basic equation. Now once you write this equation, then it's a matter of just doing it according to order of operations. Now order of operations, of course, PEMDAS. The very first thing you want to do is the stuff in parentheses. And then once you've done the stuff inside the parentheses, we have to do our exponent. So we're going to do the 1.11 to the power of 42. And then once we get that, we multiply that answer by 1,000. And so when we do that, we get an answer here of $80,087.57. Is this realistic? Yes, actually. The market over a 30-year trend, depending on which indices you're looking at or whatever, is averaging somewhere between 10 and 11%, somewhere in there. So if we are looking at 11% growth each year, if we get that, your $1,000 that you put in at the very start, after 40 years, it will become $80,000. This is the beautiful thing about compounding interest. The power of compounding interest. And I especially want you to see what effect time has in the whole picture. So we're going to ask one more question based off of the same kind of scenario. In the first case, we had this very fortunate aunt. We should all be so lucky to have such family who gave us $1,000 to be invested there. In this case, though, we're looking at what if this aunt gave us this gift when we were born instead of when we turned 18. Please figure out what that would give us. Now, everything in this situation is the same except for one factor, and that's time. So we just need to change our value of t, which of course now, since we're going from the time we're born to age 60, that's 60 years. And then we do the order of operations the same way. And we get this as our answer. $524,057.24. And again, that can really happen. These are realistic kind of numbers about what you could actually have happen as a potential here. And again, market, it does fluctuate. I use 11% here. Sometimes you might get more like 10%, sometimes more like 12%, depending on a little bit of luck and a little bit of aggressiveness in your strategy, some stuff like that. Now, as you take a look at these, I want you to note a couple things. First of all, when we go from 42 years to 60 years, notice that's not even doubling it. I didn't double 42 to get 60. Doubling 42 would take us like to 84 years. This is much less than that. And yet, notice what happened to our amounts of money. That way more than doubled. This is not a linear kind of relationship. It's not if I double time, I double my final amount. It's much more powerful than that. This is what we often describe as increasing at an increasing rate. So in other words, after year 1, you might make $10, but by the time you get to year 60, you're making, say, $10,000 every single year just from the interest, because your interest makes money on the interest, which also previously made money on the interest and so on and so forth. Hence the phrase compounding, because it's building on itself as you go. Now, if you end up fortunate enough in life to be one of the people who can give a gift of $1,000 to someone when they're born, that'd be a pretty cool gift to give to someone, right? Something good to think about. Now, for today's work, we're going to be going into looking at some graphing today. But rather than just me lecturing at you like I often would we introduce a new graphing function, we're going to do an activity instead. So having done the Desmos activity, you should have a pretty decent idea about what this graph will look like now. Like in your head, you should already be thinking that it does something like this. But as you take a look at that and are looking ahead at that, does it do that? Or does it do this? Or does it do this? What's it really looking like? Where are the points really going for this particular graph? Let's make sure that we know exactly where they go. And in order to know that, I'm going to start with the most basic way that we would start a graph, which is looking at a table, but we're not going to dwell on it very long, because we don't want to have to make a table every time anyway. And really, to fill in this table, we're just plugging in whatever the x value is for x. So like 2 cubed is 8, so I know that would be 8. 2 squared is 4. I'm just going backwards through this. 2 to the power of 1 is 2. What's 2 to the power of 0 again? It's not 0, it's 1. Which, part of the reason why I show the table here is just because it gives me an excuse to remind you of that fact and also show you why. Because notice, if I go 8 to 4, it's like I divided the 8 by 2. If I go 4 to 2, it's like I divided the 4 by 2. If I go from 2 to 1, I'm still dividing by 2. Notice, as I go up that table, I'm just dividing whatever's below it by 2 to move up the table. In fact, I could even use that to keep going and see that negative 1 gives me a half. Half of a half is a fourth. Half of a fourth is an eighth. And we can actually use all of those values. You can also get them as decimals. You could actually plug, for instance, negative 3 in there. You could do 2 to the power of negative 3 on your calculator and tell you 0.125. Or we could even know that it's 1/8, because, of course, remember what a negative exponent does, right? It flips it in the fraction. So 2 to the negative third is the same as 1 over 2 cubed, or in other words, 1/8. Now, notice the pattern here. As my x's were increasing by 1 each time, that meant that as I was going down the list of my y's, I was always multiplying by 2. What if I went the other way? What if I was going up this list? What am I doing in order to go up this list? Well, what am I doing to 8 to get 4? And 4 to 2, and 2 to get 1, and so on. Yes, we are dividing by 2. So as we go smaller on our x's, we're dividing by 2. As we go bigger on our x's, we're multiplying by 2. And we can actually see that pattern in the graph here. Because if I take a look at my graph, like I start here up 1, as I go to the right, I go to 1 to 2, and then 2 to 4. Notice the height is doubling each time. So if I'm at a height of 4, then my next height must be up 8. How high would I have to go up next time? It'd be that 8 times 2, so it'd be 16. So the next one would be up 16, and then 32, then 64. It's doubling each time, which kind of makes sense because it's 2 to the power of x, which means multiply a bunch of 2's together. Adding one more x means adding one more 2 that we're multiplying by. All right. Or you could also think about it this way. If I start at 1 here and start going to the left, I'm dividing by 2. I'm dividing that height by 2. And so this becomes a half and a quarter. You can see visually that we're actually decreasing that height. We're cutting it in half each time. Now, this is actually called an exponential. Anytime you see the variable in the exponent like this, that's what we call an exponential equation. Now, in this case, I said this is an exponential parent function rather than the exponential parent function, because there's actually lots of different ways you can write the exponential parent function. It is always some number to the power of x, but the number can change. So for instance, 2 to the x is a parent function, but so is 3 to the x, so is 4 to the x, so is even fancier stuff like 1/2 to the x. All of those would be considered a parent function because there's no like shifts or reflections or stretches or anything like that in them. Now, I want to focus on one particular part of this graph. It's what's happening as our graph is headed over here to the left. As the graph is moving left, these points, they look like they're right on the x-axis. Is this point, for instance, at 0? No. It's very close to 0 though, because remember, like if I start with 1 here, I cut that in half to get a half. I cut that in half, cut that in half, cut that in half, cut that in half. Am I ever going to take some small little positive number, cut it in half and get 0? No, I'm always going to get something, even smaller. I'm going to get something that's half as big. And it might look a lot like 0, you know, have a lot of zeros in front of it. But it's still going to be a positive number. It's not 0. And so no matter how many times we cut this in half, it's still not going to equal 0. It just gets really, really close to it. So this equation actually gives us something interesting going on. You'll notice that the lowest it ever reaches is 0, except that it doesn't actually reach 0. It gets as close as you would possibly want to get to 0 without ever actually touching it. Now that line that it's approaching here actually has a fancy mathematical name. We call that the asymptote. The asymptote is the line which the graph is approaching, but it will never ever touch, no matter how far out you go. Please add this into your formal notes. All right, so now going back to that graph that we made, you can see I added one thing to that graph. I actually drew in a dotted line for the asymptote. This is actually what we do when we make these graphs. So the actual graph is still a solid curve like we would always draw. We'd still draw that in the same way as we always would have before. But the asymptote is always dotted. The asymptote is dotted because it is a guide. It's showing something about the graph, but it is not the graph itself. And so we have to make it dotted. Only the curve is going to be solid because that's representing the actual points that were there. Now, one other little thing to note here is the way that the asymptote is written. You'll often be asked for what's the equation of the asymptote. The equation of this one is y equals 0 because you notice that that line, that horizontal line, at every point along it, the y value is the same. The y value is always 0. And anytime you're looking at a horizontal line like that, your equation will be y equals some number. Every exponential equation that you see has an asymptote at y equals some number. And it's just a number. There's no x over there because if there was an x in, then all of a sudden the line is oblique. It's no longer horizontal. Horizontal means there's no x in the equation. All right, so now we're going to tweak that equation a little bit. We're going to look at what would it be if we have y equals 2 to the power of x minus 1. Now, based on the activity that you just did, you hopefully can tell me already. What does the minus 1 do? It moves it down. Exactly, because it's hanging on the end. It's not up here with the x, it's hanging on the end. So it's going to move the entire graph down. Now what that means, in terms of some details over here, our parent function is y equals 2 to the power of x. In other words, my graph is the same as the one that I just made, except that we are going to shift it down 1. So every point is going to be in the same place, except they're all going to go down 1, which means the asymptote moves down with them. So the asymptote also moves down to -1. Remember, it was at 0, and if I take that and move it down 1, then it's at -1. When making these graphs, step 1 for making an exponential graph is draw the asymptote in as a dotted line. What we're doing by drawing in that asymptote is we're giving ourselves a new reference. Because like the first point we plot, what's anything to the power of 0 again? 1. That means that our first point is 1 above the asymptote. Now, sometimes people get mixed up by this because they're like, wait, why is the point on the x-axis? Who cares? It has nothing to do with the x-axis anymore. What I care about is only how does it relate to the asymptote. And you notice it is starting one above the asymptote. Wherever the asymptote is, we start one above it. Now, once we've done that, well, it's 2 to the power of x, right? As we saw earlier, the 2 means that we are going to double our height. So remember, this first point, it was up 1. The next point, I'd have to go up 2. And then I'd have to double that to 4. And then I'd have to double that to 8. That's as I go to the right, I'm doubling. What happens as I go to the left? Down. We divide them by 2. We cut them in half. Yep. And again, what we're cutting in half is the distance to the asymptote. It's that height above the asymptote. And then once you plotted those points, and notice, I want to plot at least a couple points on each side of that starting point. So I got a couple of them over here. In this case, I had 3 of them over here. You want to plot at least 2 on each side, because that gives you a nice idea about what the curve looks like. And that is the last thing you do is draw in that curve. Now that we have our first graph made here with transformations and everything, I want to look at domain and range. Now the domain for this graph, what do you suppose it is? Well, as we're heading off to the left here, it keeps going forever and ever to the left, getting closer and closer to the asymptote, but always headed off to the left. As we're headed up to the right, it's still going to the right. It gets really, really high up there, but it's still going to the right. So yes, your domain is all real numbers. But the range, it's not. Because you'll notice the range, it starts here. And it's everything that's above that. So range, of course, range is talking about our y values. And in this case, my y values are starting out at -1. But what goes between those two? It's above, so it's greater than. But remember that it never actually equals -1. So this, for the first time, is one where we can see that the range is y is greater than -1 and not equal to. For the very first time of all the different function types we've used up to this point, they were equal. This one is not. Because remember, it gets as close as you might want to -1, but it never actually reaches it. That's that whole idea of the asymptote. All right, one last one that we're going to take a look at. We saw what happens with the 2 to the power of x, how we're doubling it and all that kind of stuff. Now, if it's 3 to the x, what happens when we change that base? Well, first of all, in this particular example, I'm not applying any transformations to it. So the 3 to the x is our parent function. And because there's no transformations in it, my asymptote's still at 0. And my first point, remember the first point is always up 1. Because anything to the power of 0 is 1, including 3 to the power of 0. So I always start that same way. Now, once I've done that, the question is, where do I go from there? Well, when it was 2 to the x, and I was headed to the right over here, I doubled my height. What do you suppose we're going to do here? We're going to triple our height. What do you suppose we're going to do as we head to the left? Well, before we cut them in half, that is, we divided them by 2, so now we divide by 3. Yes, that's a typo up there. That's supposed to be a 3 there. Divide by 3 as we go to the left. And by doing that, you can plot the points, and once you plot the points, you can go ahead and draw your graph through. Last thing here, domain and range. What's our domain on this graph? All real numbers, absolutely. What's the range going to be then? Y is greater than 0. Not greater than or equal to, just greater than, because of course 0 is the asymptote and we never really reach the asymptote.